Imagine standing outside on a bright afternoon, feeling the sun's warmth on your face and the gentle movement of air against your skin. That simple sensation is the surface expression of a vast planetary engine that has been running for billions of years. Every second, Earth intercepts an enormous stream of energy from the Sun. That energy does not simply sit still. It absorbs, reflects, converts into heat, carries by winds and ocean currents, stored in water vapor and ice, and eventually return to space as an infrared radiation. The continuous movement of this energy through the atmosphere, oceans, land, ice, and living system forms the global climate system. Without the precise balance between energy arriving and energy leaving, temperature would swing wildly and life as we know it would be impossible. Satellites circling the planet measure the incoming sunlight and the outgoing heat with remarkable precision. Ocean sensors track how much exceed heat is stored in the deep sea. Weather balloons and ground stations record temperature and humidity patterns that reveal how energy is redistributed from the tropics towards the poles. Together, these observations paint a clear, consistent picture of a planet whose climate is powered by solar energy and regulated by interlocking circles of radiation, motion, and phase change. In the page that follow, we will walk through the picture in detail, using everyday language and the hard numbers that science has established, so that the workings of Earth's climate system become as understandable as the warmth you feel on a sunny day. The sun delivers energy across a wide spectrum of wavelengths, most of it in the visible and near-infrared range. And the planet's response to the energy determines everything from daily weather to long-term climate stability. Because Earth is a sphere rotating on a tilt axis and orbiting the Sun in a slightly elliptical path. The amount of energy received at any location changes with latitude, season, and time of day, creating the fundamental gradients that drive atmospheric and oceanic motion. At the equator, the sun sits high in the sky throughout the year, delivering intense energy nearly every day, while at the poles, the same sunlight arrives at a low angle or disappears entirely for months, producing the stark contrast that forces the entire climate system to transport energy from places of surplus to places of deficit. The journey of energy begins at the top of the atmosphere. Average over the entire globe and over a full year, sunlight arrives at a rate of roughly 340 watts for every square meter of Earth's surface. That figure is not intensity of the beam hitting a surface pointed straight at the sun. It is the total solar power spread across the sphere of the planet, day and night, equator and poles. The actual intensity of sunlight at the distance of Earth's orbit is about 1,360 watts per square meter when measured on a surface facing the sun directly. But because only half the planet is illuminated at any moment, and because the rays strike most latitude at an angle, the global average falls to 1/4 of that value. Of those 340 watts, about 100 watts are reflected straight back to space. Clouds, bright ice and snow, desert sands, and tiny particles in the air do most of the reflecting. Thick, low clouds can reflect more than half the sunlight that hits them, while fresh snow can reflect up to 90%. Dark ocean water reflects only a few percent, and forests reflect roughly 10 to 50%. The planetary average reflectivity, known as albedo, is therefore close to 3 to 30%. The remaining 240 watts are observed. Roughly 77 of those watts are taken up by the atmosphere itself, by ozone high up, by water vapor and dust lower down. The other 163 watts reach the surface and warm the land and the upper layer of the oceans. This absorbed energy does not stay where it lands. The surface radiates heat upward as infrared radiation according to its temperature. At the same time, water evaporates, carrying latent heat into the air, and warm air rises, carrying sensible heat. The atmosphere absorbs most of the infrared radiation, leaving the surface, then re-emits it in all directions, some upward toward space and some downward back to the ground. The downward stream is what we call the natural greenhouse effect. Without it, the average surface temperature would be about minus 18 degrees Celsius. With it, the average is roughly 15 degrees Celsius, warm enough for liquid water to cover most of the planet. The difference of roughly 33 degrees Celsius is a direct measure of how effectively the atmosphere traps and returns heat. The surface itself emits roughly 390 to 400 watts per square meter of infrared radiation on a global average. Yet, only about 240 watts of that energy ultimately leave the planet after the atmosphere has absorbed, reprocessed, and redirected the majority of the upward stream. Greenhouse effect is not a single gas acting alone. Water vapor is the strongest absorber of infrared radiation under present conditions, followed by carbon dioxide, methane, and several other trace gases. Each molecule has a unique pattern of absorption, bands, determined by its structure and the wavelengths of the energy it can absorb and re-emit. Water vapor absorbs strongly across broad stretches of the infrared spectrum, yet it leaves certain windows partially open. Carbon dioxide absorbs in some of those remaining windows, particularly around wavelengths of 15 micrometers, and methane fills other gaps. Where those bands overlap or fill gaps left by other gases, the atmosphere becomes more opaque to outgoing heat. The result is that the altitude from which Earth finally radiates energy to space is higher and colder than the surface, because colder objects emit less radiation according to the fourth power relationship between temperature and emit energy. The planet must warm a little so that the higher, colder layers can still send out as much energy as the sun supplies. This radiative balance is measured continuously by satellites that detect both the shortwave sunlight reflected and the long-wave heat emitted. Instruments on these satellites scan the entire planet many times each day, building a global map of energy flows with an accuracy of a few tenths of a watt per square meter. When the two numbers match, the climate is in equilibrium. When they do not, heat accumulates or is lost. The height at which the atmosphere becomes transparent enough for infrared energy to escape freely is typically several kilometers above the surface, and the temperature at that level is substantially lower than the temperature at ground level, locking in the warming effect that makes the lower atmosphere and the surface livable. At present, the measurements show a small but persistent imbalance. Earth is absorbing roughly 0.8 to 1 watt per square meter, more than it is radiating back to space. More than 90% of that extra energy ends up in the ocean, because water has a high heat capacity and covers most of the planet. A single watt per square meter may sound small, yet when multiplied by the entire surface area of Earth, it represents hundreds of trillions of watts of continuous heating. The remainder of the excess energy warms the land, melts ice and raise the temperature of the lower atmosphere. These numbers come from multiple independent methods. Satellite radiometers that measure radiation at the top of the atmosphere. Deep ocean temperature profiles collected by thousands of automated floats that dive and rise through the water column. And the observed rise in sea level caused by thermal expansion of sea water, and they agree within a narrow range of uncertainty, because the ocean stores heat so effectively. The full surface temperature responds to any change in energy balance lag behind the imbalance itself by years to decades. The upper few hundred meters of the ocean hold the bulk of the recently added heat, while deeper layers gradually take up a smaller share over long periods, creating a delayed but lasting influence on the climate system. Energy does not simply accumulate where it is absorbed. The tropics receive far more sunlight than they emit as infrared radiation, while the polar regions emit more than they receive. In the equatorial zone, the annual surplus can exceed 100 watts per square meters, while near the poles, the annual deficit reaches similar values. The difference must be carried poleward by the atmosphere and the oceans. Otherwise, the equator would grow ever hotter and the poles ever colder. The atmosphere moves energy in several ways. In tropics, warm, moist air rises in towering thunderstorms, releasing latent heat, when water vapor condenses into liquid droplets or ice crystals. That heat is then transported poleward by the large-scale overturning cells known as the Hadley circulation. Air rising near the equator travels toward higher latitudes in the upper troposphere at altitudes of 10 to 15 kilometers, sinks around 30 degrees north and south, where the air becomes cooler and denser, and returns toward the equator near the surface as the trade winds. The sinking air warms by compression and produces a subtropical dry zones that contain many of the world's deserts. Between roughly 30 to 60 degree latitude at different cells, the ferrocell operates in the opposite sense, with air rising near 60 degrees and sinking near 30 degrees, driven largely by the eddies and storms of the mid-latitude rather than by direct thermal forcing. Beyond 60 degrees, the polar south completes the three-cell pattern in each hemisphere, with cold air sinking over the poles and flowing equatorward near the surface. Superimposed on the south are the jet streams, fast rivers of air in the upper troposphere that meander and can shift the paths of storms by hundreds of kilometers. Mid-latitude weather systems themselves are efficient energy transporter. Warm air moves poleward ahead of cold fronts, and cold air moves equatorward behind them, exchanging heat on a grand scale through a continuous process of mixing and stirring. The combined effect of these atmospheric motions moves roughly half of the required poleward energy transport, with the remainder carried by the oceans. The oceans carry roughly half as much heat poleward as the atmosphere does, but they do so more steadily and over long time scales. Surface currents driven by the winds move warm water away from the equator in broad gyres that circle the major ocean basins. In the Atlantic, for example, a continuous flow of water travels northward, releasing heat to the overlying air along the way and moderating the climate of nearby land areas. The deep ocean, a slower circulation, is driven by differences in density caused by temperature and salinity. Cold, salty water sinks in a few key regions at high latitudes where surface water becomes dense enough to descend, then spreads through the deep basins of the world's oceans, eventually rising again in distant parts of the world after centuries of travel. This overturning helps store heat for long periods and mix nutrients that support marine life. But its primary climatic role is the redistribution of energy from low latitude to high latitude and from the surface into the deep ocean. Because the deep ocean contains the vast majority of the planet's heat capacity, even small change in the rate of this overturning can affect how quickly excess energy is sequestered away from the surface. The surface mix layer typically tends to a few hundred meters deep, exchange heat with the atmosphere on seasonal time scale, while the deeper layers respond far more slowly, acting as a long-term buffer that smooths out short-term fluctuations in the energy balance. Water itself is a powerful energy carrier. Evaporation at the surface absorbs roughly 80 to 90 watts per square meter of latent heat on a global average, turning liquid water into vapor and locking that energy into the molecular structure of the vapor. When that vapor later condenses into clouds or rain, the same amount of heat is released into the atmosphere, often thousands of kilometers from where the evaporation occurred. This latent heat pathway is especially important in the tropics, where the energy released by condensation fuels the strong upward motion of Hadley cells and the monsoon circulation that brings seasonal rains to large regions of Asia, Africa, and the Americas. The water circle, therefore, is not merely a circle of moisture. It is an integral part of the planetary energy circle. Changes in temperature alter the amount of water vapor the air can hold, according to the well-established physical relationship. Warmer air holds more moisture. Temperature rise of 1 degree Celsius increase the water holding capacity of the atmosphere by roughly 7%. That extra vapor both carries more latent heat and strengthens the greenhouse effect. Because water vapor itself a greenhouse gas, that feedback is one of the strongest amplifiers of temperature change in the climate system and is observed both in the modern instrumental record and in paleoclimate reconstruction. Condensation and freezing also release heat at different rates. So the formation of ice crystal in high clouds versus liquid droplets in lower clouds produce distinct thermal effects that further shape the energy flows within the atmosphere. Ice and snow play a dual role. Their high reflectivity albedo values of 0.6 to 0.9 means that expanding ice sheets or seasonal snow cover reflect more sunlight and cool the planet further. Contracting ice does the opposite, allowing darker ocean or land to absorb more energy. Fresh snow can reflect 80 to 90% of incoming sunlight, where bare sea ice reflects about 50 to 70% and open ocean reflects only 5 to 10%. When sea ice melts, the sudden drop in reflectivity can increase local energy absorptions by tens of watts per square meters. This ice-albedo feedback is especially strong at high latitudes and helps explain why polar regions warm faster than the global average. When the energy balance shifts, measurements from satellites show that the area of Arctic sea ice has declined markedly over recent decades, reducing the planet's overall reflectivity and adding a positive contribution to the energy imbalance. Seasonal snow cover on land also influence the energy budget, particularly in the northern hemisphere, where large continental areas experience snow for parts of the year. The timing of snow melt in spring affects how early the land surface begins to absorb stronger sunlight, feeding back onto regional temperatures and atmospheric circulation. Ice sheets on land store water over millennia, and when they gain or lose mass, alter both the reflectivity of the surface and the amount of fresh water entering the ocean, which in turn can influence the density-driven overturning circulation. Land surfaces also matter. Forests absorb more sunlight than deserts or grasslands, yet they also cool the air through evaporation of water from leaves, a process that transfers latent heat upward. Dark soil absorbs heat readily. Light-colored soils reflect more. Urban areas with dark roof and pavement absorb more energy than surrounding rural landscape, and often create local heat islands. Human alteration of land cover, clearing forest, expanding city, irrigating croplands, therefore changes the local and sometimes regional energy budget by altering both albedo and the portioning of energy between sensible heat and latent heat. These changes are smaller on a global scale than the effect of rising greenhouse gas concentrations, but they are measured and are included in modern climate calculations that track energy flows at regional resolution. The contrast between a dense forest canopy and an open field that can shift the local surface energy balance by tens of watts per square meter, demonstrating how even modest change in surface properties cascade through the climate system. All these processes, radiation, evaporation, condensation, and atmospheric overturning, ocean currents, and ice-albedo change, interact continuously. A shift in one component produces response in the other. The climate system as a whole can be viewed as a set of coupled reservoirs of energy linked by fluxes. The atmosphere is a thin, rapidly responding reservoir that adjusts on time scales of days to weeks. The upper ocean is thicker and slower, responding on time scales of months through 2 years. The deep ocean and the ice sheets respond on timescales of decades to millennia. Because of these different response times, the full effect of a change in energy balance is not felt immediately. Heat that enters the ocean today will continue to influence surface temperature for many years as it is gradually mixed upward or carried by currents, clouds, and further complexity because they both reflect sunlight and trap infrared radiation. The net effect depends on altitude, thickness, and geographic location. Low clouds tend to cool the planet by reflecting sunlight, while high thin clouds tend to warm it by trapping heat. Changes in cloud patterns therefore represent an important but still actively studied feedback within the energy circle. The interplay among these reservoirs and feedbacks means that the climate change does not respond in simply linear fashion. Small shifts in one flux can be amplified or damped by the response of the others, producing the complex patterns of temperature, rainfall, and circulation observed across the planet. Scientific confidence in this picture rests on multiple lines of evidence. Satellite instruments measure the radiation budget at the top of the atmosphere with an accuracy of a few tenths of watt per square meter by detecting both reflected solar radiation and emitted infrared radiation across the entire planet. Ocean profiling floats map temperature and salinity throughout the upper 2,000 meters from the global ocean, revealing the accumulation of heat with high spatial and temporal resolution. Surface weather networks and radiosondes document the temperature and humidity structure of the atmosphere, allowing calculation of how much energy is transported by winds and storms. Paleoclimate records ice core that preserve ocean air bubbles and isotopic signature, ocean sediments that record past temperature through chemical radios, tree rings that reflect growing season conditions, and corals that achieve seawater temperatures show that when natural factors such as change in Earth orbital geometry or large volcanic eruption alter the energy balance in the past, the climate responds in ways consistent with the same physical principles that operate today. Computer models that solve the fundamental equation of fluid motion, radiation transfer, and thermodynamics reproduce the observed pattern of temperature, precipitation, and circulation when they are given the observed energy flux as input. When the same models are run with the measured increase in greenhouse gases, they produce an energy imbalance and a warning pattern that match the observation of the past century within the range of natural variability. The consistency across these independent lines of evidence, from direct radiation measurements to ocean heat content to paleoclimate achievements, provides strong confirmation that energy circle is both way quantitatively understood and reliably described by established physical laws. The number of themselves are robust. The 340 watts per square meter of incoming solar radiation is known from direct satellite measurements of total solar irradiance combined by the geometry of Earth orbit and rotation. The 30% planetary albedo is measured by the same satellite looking at reflected sunlight across all latitudes and seasons. The partitioning of absorbed energy between atmosphere and surface is constrained by both radiation measurements and the observed surface energy flux of latent heat, sensible heat, and net infrared radiation. The magnitude of greenhouse effect is calculated from the difference between the infrared radiation emitted by the surface and the infrared radiation that ultimately escapes to space. That difference is about 150 to 160 watts per square meter under present condition. That difference is about the current energy imbalance of roughly 0.9 watts per square meter is detected both from the radiation budget at the top of the atmosphere and from the rate of heat storage in the ocean. These independent estimates converge, giving high confidence that the planetary energy circle is understood in quantitative detail. Seasonal and regional variation and further richness. The energy surplus in the summer hemisphere is larger than the winter hemisphere, giving the annual migration of atmospheric circulation features and the seasonal build-up and release of heat in the upper ocean. Day-to-night contrast further illustrate the system responsiveness, with the surface cooling rapidly after sunset while the ocean retains heat far longer, moderating temperature swing over water compared with land. Understanding the global climate system and its energy circle is not merely an academic exercise. Every weather pattern, every seasonal shift, every long-term change in temperature or rainfall is an expression of how energy is received, stored, moved, and released. The same physical principle that keep the tropics from overheating and the poles from freezing also determines how the climate will respond to any future change in the energy balance. By measuring those fluxes carefully and tracing their pathways through the atmosphere, ocean, ice, and land, science provides a clear and consistent description of the machinery that maintains the climate of our living planet. The warmth on your skin, the rain that falls, the winds that blow, and the slow currents that circle the ocean basins are all parts of one continuous energy story, one that satellites, ships, and ground instruments continue to read with ever greater precision. And as measurements improve and record lengthen, the quantitative picture of Earth's energy budget becomes sharper, confirming that the fundamental processes of absorption, reflection, transport, and emission govern the climate system at every scale, from local daily cycles to planetary multi-decadal trends. The interlocking nature of these processes ensure that no single component operates in isolation. Each flux influences the others, creating a self-regulating yet responsive system whose behavior can be tracked, quantitative, and understood through careful observation and application of basic physical principles.